Hello to all of you. My name is Gianmario Verona, and I'm rector of Bocconi University. I'm speaking from one of the classrooms here on campus where we should have been together physically to enjoy our elegant city, Milan, and the academic atmosphere of Bocconi University. Thank goodness the internet enables us to enjoy the conference in the innovative format despite the difficulties of traveling for most of us. It is for me a distinct pleasure to introduce the Fisher-Schultz lecture of the 2020 Econometric Society World Congress. This year, the distinguished speaker is Professor Esther Duflo, the Abdul Latif Jamil Professor of Poverty Alleviation and Development Economics at the Massachusetts Institute of Technology. As you all know, together with Professors Banerjee and Kramer, she's one of the 3 recipients of the 2019 Nobel Prize in Economics. I am particularly pleased to introduce Professor Duflo for 3 reasons. First of all, for her impact on the field of economics. We have a motto at Bocconi University that applies to all of our 8 departments. We strive to produce knowledge that matters. And I believe that the work of Professor Duflo clearly answers this call. As many of you know, the experimental method she pioneered in her research based on randomized controlled trials is not only technically rigorous, but has produced fundamental innovation in testing development policies. Even more importantly, her ability to make it available to many policymakers is particularly relevant in academia, where sometimes we are criticized for living in an ivory tower. The second reason is the influence of her work in the debate on sustainable capitalism. As a professor of management myself, I cannot avoid noting how topics like poverty alleviation and economic development are becoming crucial to stimulate action towards envisioning a new form of capitalism. A form that can preserve the fundamental engine, but at the same time find tools to care for others. And the current pandemic that is keeping us apart has tragic consequences on the same specific social classes in diverse countries. This demonstrates how we need to rethink many of these mechanisms. So Professor Duflo's work must also be praised for this reason. But there is a third reason why I'm particularly pleased: her friendship towards Europe and Bocconi in particular. Despite working in the United States, she's been constantly in touch with Europe, for instance, serving for many years as director of the Development Economic Group at the CEPR. She has also always been very close to Bocconi and to her fellow development economist, Professor Eliana La Ferrara. She has played an important role in the launch of the Bocconi LEAP laboratory, an initiative inspired by Jay Powell at MIT. Overall, Professor Duflo is a role model in academia for young scholars and for women in particular. One day, I wish to welcome you all to Milan. In the meantime, I'm sure you will enjoy her presentation.
Good afternoon if you are in Milan. Good morning, good night, good evening if you are everywhere in the world, as many of you probably are. This is a great pleasure and a great honor to be giving this Fisher-Schultz lecture. I very much regret to not be in person at Bocconi to give it, but this is nonetheless a new experience and something that I look forward to share with you. What I'm going to talk about today is the confluence of machine learning and randomized control trial, and the title of the lecture is Generic Machine Learning Inference on Heterogeneous Treatment Effects in Randomized Experiments with an Application to Immunization in India. This is joint work with several others. The explosion of RCT and machine learning are arguably 2 of the most important developments for applied economists in the last couple of decades. This is probably a repeat if you just attended the policy session that took place before that, but I think it's worth giving the context for anybody who might not have attended those lectures. A priori, you might think that RCT and machine learning have nothing to do with each other because in the case of randomized control trial, you might be targeting a single parameter in a very well identified circumstances. So there is one regression to be run. or one set of means to compare, and you really get nothing different. But in fact, in the real world, of course, nothing is as simple as the basic, fully randomized model. And in fact, applied RCT researchers such as me are often confronted to problems that lend themselves very well to using machine learning methods, particularly when we are looking to apply randomized control trials to very large experiments with the idea of becoming directly useful to policy. So you may have many covariates to choose from to control and make sure that your treatment and control groups are actually completely comparable. You may have many treatments. You may have very many outcomes, and you may have very many subgroups by which you might want to compare those variables. And all of these problems, basically, as soon as the word many starts showing up, then the idea of machine learning is never very far behind. So conceptually, the trade-off that an applied RCT researchers might, or an applied economist in general might encounter is between being very specific, so being an oracle, you know something. So you, for example, have a very specific idea of what background variable might be relevant to the outcome. So you will run a perfectly stratified experiment. You will choose one or two specified outcomes, one or two treatments, and one or two subgroups by which you are going to analyze your data. You're going to make sure that your sample size is adequately powered to measure all of the contrast you're interested in. And you're going to write a very detailed pre-analysis plan where everything is going to be set up from the beginning. And then you can just let the data guide the analysis. Now, if you happen to be an oracle, if you happen to know almost everything, then you are in perfectly good shape. And this is how you should get going. And in a sense, this is very much the direction that the medical world has taken, or at least had taken before they were also caught up by data science and machine learning, when they were asking their researchers to basically stick to very simple design when you have one unique contrast, and write down everything they wanted to do in advance in a pre-analysis plan. And part of economics has also gone this way. The issue is that you end up losing a lot of potential information or real information. So when I'm saying potential information is, for example, if you have you are considering affecting an outcome, say immunization, which is what we are going to talk about today, and you have many ideas of what might work based on prior literature. So you have kind of basically a fork in the road. You could say, well, this is too many potential treatments. I'm just going to choose one and really put all my eggs in this one particular basket and run this one contrast. So you behave as if you are the oracle, and there is only this one last piece of information you don't know, which is what the effect of this particular treatment or combination of treatment is in your sample. So there you give up a lot of potential information because you have not even run the richer experiments. The nice aspect of having given up this information is that you're going to get a very precise answer about what you are testing. But there are all these other things you could have known that you will never know. The dimension in which you lose real information, you can lose real information, is once you've collected, for example, very rich baseline variables, you could be interested in looking, say, at whether the effect of the policy is heterogeneous, which might be very relevant in a lot of cases. It might hurt in some places and help in some other places. So it's something you might want to know. But again, if you want to stick to a very specific pre-analysis plan, you would have to say it from the beginning, and you have to limit the number of contrasts. Otherwise, the demand on your data are too infinite to look at everything in details. So there you might have the information and decide not to use it ex ante. So this is the sense in which you're losing real information in this way. That's one way you could go. So it's basically this very much analogous to imposing a lot of structure to how you look at your data versus having a much more data-driven approach. So you might want to let the data decide what might be relevant. So instead of running one treatment, you might want to run many and see who wins. Instead of just looking at treatment versus control in the population at large or in one pre-specified subgroup, you might want to have many subgroups. Let the data decide where the intervention is most useful or least useful. But then you run the risk of specification searching, which is, of course, a huge problem. If you run 100 regression, 5 of them are going to come out significant. And you, of course, won't have any way to be sure that what you report is actually real as opposed to being a fluke. And that is if you're perfectly benevolent and really are trying to do the right thing. So you need to find a way to preserve that richness in the data without running into this risk of specification searching. And this is where machine learning tools come in. They seem a priori a very attractive way to think about this type of problems, because you can pre-specify not a particular contrast or comparison, but a particular algorithm that is going to let the data speak. So you are tying your hands, but you're not tying your hand to a specific set of analysis you will run, but you are tying your hand to how you're going to use the data to find out what works the best and where, for example. So for this reason, the machine learning tools have become quite popular in the analysis of experiments. I think I would really want to credit Susan Avey and Hilo Imbens for having done a lot to popularize their use and develop the method that goes with it, starting with their chapter on randomized controlled trial in the Handbook of Field Experiments, and then a lot of papers on methods and summaries as well. So this is also an agenda that I've become very, very interested in working, and the way that I tend to address problems that I don't know very much about is that I seek out my colleagues or the brighter students we have in the department. And so I've engaged into kind of asking questions to basically Victor Chernozukov and Ivan Fernandez-Val and Mert Demirer to kind of explore one by one what could we do about all of these problems and how to address them. So today I'm going to focus on one such problem, which is the discovery of heterogeneity in the impact of randomized controlled trial, and try to show you how we apply it to a real important policy issue, which is immunization in India. So I'm going to spend maybe less time on the methods itself and a little bit more time on the application, because I really want to convince you that the reason why I'm engaged in this work is because I think it is useful, it is important, it's going to make a difference in the real world. So heterogeneity is often a key element in treatment effect models. Typically, the way we are going about it is to report the average treatment effect in subgroups. Machine learning would seem to be very appropriate to looking for these things, because for this heterogeneity, because it's good, we know at looking for patterns, for heterogeneity recognition in high-dimensional settings. But the problem is that there are a lot of difficulties, in fact, in implementing them in practice. So we kind of would really love to use machine learning tools, but when we get to the business of it, it becomes a little bit more complicated in practice than just pressing a button for regression or a comparison of means. So what we are doing in this work is to provide a very practical way forward to these challenges for the discovery of heterogeneity in randomized experiments, something which we hope is going to be of practical use. So just to set up the stage a little bit, some notation. So imagine you have potential outcomes, Y1 and Y0, Y1 for treatment and Y0 for non-treatment, and a vector of covariates, which might be the variables by which there might be some heterogeneity. So the main causal functions are the baseline conditional average, E of Y0 given Z, and the conditional average treatment effect, or CAT-A, which is the difference between the expectation of Y y1 given z and y0 given z. We are going to continuously assume that we have a randomized experiment. It could be that the propensity score depends on the z, but it's a known function of the covariance. Okay, so we have a knowledge of the propensity score. It could be a half, or it could be something different, but it's known. We also assume that the propensity score is bounded away from zero of unity. And under this assumption, you could write down the causal function as y is b0 of z plus d times s0 of z plus u, where d is an indicator for being in the treatment group. We have data, which is the data we observe, where we have the outcome variable y, the covariate z, and whether or not we have a treatment. Observation is treated or control, and we are interested in the heterogeneous Kt function or conditional average treatment factor. So it becomes very tempting when we don't know, we have potentially many variable z to say, or high dimensional vector z to say, well, we are going to use machine learning. What's machine learning? It's kind of a catch-all word here for evolving a set of evolving statistical learning methods. Forests and trees are very popular in economics. There are others. They keep moving. There are new ones coming up all the time. And we know, of course, that they work very well in practice for prediction purpose, much better than classical method in high dimensional settings. So we could try and approximate the Kt function via machine learning methods, but the difficulty is that we basically, it's going to be fundamentally difficult without a set of fairly restrictive assumptions to obtain consistencies, and even harder to get inference for the conditional average treatment effect using machine learning. This is nothing that's new. This is something that's, of course, very well known, which is basically if the dimensionality of Z, the potential set of covariates, is something that's even rather modest, so greater than log of n. So, for example, if D is 5 and we have 10,000 observations, that's already in that ballpark. Then you have no consistent machine learning estimator of Z. It means you cannot estimate, you cannot produce parameters of this function. You could, so of course the way that you can get away with this is to assume sparsity, but that's something, for example, that underlies lasso and other methods, but sparsity is untestable, so it might apply or it might not apply. For example, in the case of heterogeneity, at some level, you might not be in a position to say that for sure that the treatment effect is the same in most of the subgroups, but you just don't know which one. Like in many cases, this is not an assumption. This is very attractive, and you don't want to make sense of that. Even if you assume that you still would have difficulty getting confidence intervals. In addition, suppose that you were willing to make strong assumption for that will guarantee ML consistency and valid inference. You still need to do it in practice. And the issue with machine learning, partly because it's new and partly because it's not been fully translated to our social sciences, is that the real implementation of this algorithm is very black boxy, and it's a giant engineering effort. So the justification is often based on practice. It's a little bit unclear whether even in the theory, if you were in the best theoretical work, the gap in particular for applied researchers between what you might do in practice and what would be necessary for the methods to actually work might be very large. So that's kind of an additional problem, which I think is very pertinent for the applied researchers, on top of the other, more fundamental problem we discussed before. So what we propose instead is sort of to sidestep this problem by being less ambitious. So basically, we are not going to be able to give you the full conditional average treatment effect. But what we can do is to get some object, some feature of the conditional average treatment effect, which might be of interest to a policymaker or to an applied researcher. So basically, the way we solve this trade-off is by being much less ambitious in terms of what we are trying to pick up, but by that this is going to instead allow us to use machine learning and still get consistency and inference for these much more limited objects that we are going to get after. So our approach is generic with respect to the machine learning methods. It will work with any that you like. And we use this double machine learning as our key tool. So in terms of literature that it relates to the use of double machine learning, in particular our previous work where we introduced, we used double machine learning to control for nuisance parameter while trying to estimate a single causal parameter. So that's one set of literature that this work relates to. Another set of literature relates to various efforts to estimate heterogeneous effects. Very important work by using trees by Etienne Imbens and then Wager et. Previous work by Vector looking using sparsity. So these were kind of the different approaches. They are not better or worse, but there are different approaches to get to the same issue. So in the first step, so this works, basically the method works in two steps. In the, we will split the data into a main sample and an auxiliary sample. We'll do that many, many times. So we are going to have a series of random split into a main sample and an auxiliary sample. In the auxiliary sample, we obtain generic machine learning estimates of the baseline and treatment effect, which we'll call the baseline proxy. So we'll have a baseline proxy for the BZ function and a baseline function proxy for the SZ function, which is the proxy for the conditional average treatment effect. This can be done with any method, and we can throw several methods at the problem and compare their performance. We are not going to assume that those are consistent. We are going to, for us, they are just biased and at worst biased and at best noisy predictor, both of the B0 of Z and S0 of Z function. So that's where the second step come in, which is in the main sample, we are going to target key feature of the conditional average treatment effect. One is the best linear predictor of the Kt S0 using the ML proxies. So that's going to be mainly useful to tell us whether there is any heterogeneity or what we thought was heterogeneity was just a fluke that we found in our auxiliary sample. We can also look at a group average treatment effect sorted by the group induced by the ML proxy S of Z. So basically, we are going to have the treatment effect for the least affected quintile and the second to least affected quintile going to the most affected quintile. And then what we call classification analysis, which is comparing the characteristics at a purely descriptive level, comparing some characteristics of the most of the units in the most and least affected group. Note that you have to be very careful with the interpretation of this CLAN data, because if you take it too seriously, it becomes, you're back to problem number one, which is you're back to ascribing a structure to data that is descriptive. But at least if you have shown that there is in fact heterogeneity in the data that is well predicted by your Z variables, and that you have your most affected group is much more affected than your least affected group, you can at least describe what this group look like, which is useful potentially to understand what is going on, and also, and most importantly, to guide future practice. So the objective of our paper is to estimate and develop valid inference for these features in the main sample. So how do we proceed? So if you consider the weighted linear projection of Y on a treatment effect, and then a treatment indicator, or treatment minus the propensity score, if the propensity score is not constant, and the treatment indicator interacted with the S function, then our first theorem is that this projection coefficient identify the best linear predictor of the conditional average treatment effect. And in particular, you have some interesting special cases. So if what's been estimated and what is being discovered in the auxiliary sample is a perfect prophy for the true kt, then beta 2 will be 1. In general, it's not going to be 1 simply because some of what's being picked up in the auxiliary sample reflect overfitting and noise. If S of Z is complete noise, then beta 2 is going to be equal to 0. And that's a very important step, because what you might, in many applied cases, your investigation might stop there, which is you realize that, so if you just look at your data and you say, oh, let me run a couple of subgroups, and then something comes out and that looks interesting, but they were not necessarily pre-specified. I think you want to do this step as a reality check and say, well, this could just, if beta 2 is 0, then this was just noise. The estimation is done through the empirical analog. So very, very simply, once you have your predicted S function from the auxiliary sample, you regress, you go back to the main sample and run this regression with the predicted kt. So what's nice in that setting is that this is a very easy regression to run. You can introduce fixed effect, you can introduce cluster standard error, you can have strata, you can have randomization different probability of randomization that's captured by the propensity score, and so on and so forth. So this is very easy to run. Once you have done that, and if you're satisfied that your beta 2 is not 0, so you actually have you seem to have some heterogeneity that you're capturing from with the covariates that you do have, you can start asking yourself the question, okay, what's the treatment effect for the most affected group and the least affected group and any in between? So basically what you're looking at is the treatment effect by, say, 5 group, 1 to 5. So you build a group to explain as much of the variation in Z as possible. So you divide your data in the support of proxy into K groups, could be 5 groups, 5 quintiles, for example. And then it's very simple, the linear projection on indicator for belonging to these groups based on your Z's is what you're going to interact with your treatment variable, and the projection coefficient will identify the group average treatment effect as well. So for example, you might run it this way, where you have you have 5 groups. You're running you have the true, in these are simulations, we know what is the true group average treatment effect, and then you're seeing in blue the estimated GATEs in this data using this technique. Finally, once you have your least affected group and most affected group, you would be interested in a vector of characteristic of a unit, typically the uninteracted Z's. And the parameters are the average characteristic of those. So the income in the most affected group and least affected group, or in the case we are going to look at today, the prior immunization rates in the villages between the most affected and the least affected. So once you have, so this, until now I've shown you how we go about estimating these things. Of course, we now want to get confidence interval for them. We want to get inference for them. There are many things that one might be interested in. You want beta 2. You want the different grouped average treatment effect. You want the difference between the baseline variables. So if you had only one split, in a sense, that would be trivial. There is nothing different. Since you're running your regression you have in your main sample, you basically can recover the treatment effect from that. Unfortunately, what this forgets is that by splitting your data, you have added another source of uncertainty. Because, well, you could have used another split. So conditional on the data split, the estimation uncertainty is completely standard. But to account for uncertainty induced by data splitting is actually important. Because you could have one split. First of all, you could choose your split. Second of all, which would be sort of malevolent. Second of all, you could be unlucky with your split. So that's the problem we are trying to solve. And how we are going to solve it, instead of doing one split, you're going to do many splits, and then you're going to pick the median of the confidence interval. So if you had only one data split, the inference is completely usual. There's nothing special with the confidence interval. The same theory as usual applies. But data splitting induces its own risks or arbitrariness. Two researchers could well draw different conclusions from the same data just because they picked a different split, even if they specified it in advance. Researchers could also tinker with the split. We're hoping it doesn't happen. But researchers who have honestly fixed the seed in advance are subjected to the risk that the split may be non-typical and you get something not what you expected, or you get something funny. So to avoid these risks, you rely on multiple splits, and then you take median of your confidence interval over the splits. And then so one sort of side step, but an important step in that paper, is to quantify the uncertainty induced by the random splitting. So unfortunately, because you have to split the data, and that introduce not only that cuts your sample in two, but you have introduced additional uncertainty by the way that you've split it, and you need to account for that uncertainty. And I'm going to skip the details of that, but what's basically, if you want to see the bottom line, is that the confidence level is going to be discounted roughly from 1 minus alpha to 1 minus 2 alpha. So this is basically makes you, if you pick your alpha of 0.05, you're going to report 90%. What we would be used as the 95% confidence interval would become 90% confidence interval. So that's sad. I think it's something that is very important for us applied researchers to remember, which is none of that comes for free in terms of data requirements. So if you're interested in discovering heterogeneity and you do not want to put much structure on the data on where to look for it, then the sample size will have to be larger. So provide some simulation in the data, which basically suggests that it should be about something like about twice as large a sample size to be able to discover heterogeneity relative to a situation where you would be interested in powering a particular simple treatment effect. But of course, this is going to depend on a lot of things, and the multiply by 2 is just a rule of thumb. I'm going to skip that. I gave you the bottom line already. So now I want to talk about an application of this, which is, to me, not just an application to show that, well, this is working, it can actually be run, but it's an application which is of extreme importance to policy in general, and in my life has been kind of with me almost continuously since I've started working on economics and working on India in particular, which is the issue of immunization. So of course, we are all thinking about health these days, and you're all thinking about COVID-19. But despite COVID-19, I want you to, if you have one thing to remember from this talk, just remember that the under-immunization remains one of the key health challenges that the world has to deal with. The WHO estimates that every year you could save 1.5 million deaths if the global immunization coverage improved from 85%, which it is today, to about 95%. Every year, about 20 million kids under the age of 1 don't get DTP vaccine. That's data for 2018. And many of these kids live in 10 countries, including India, which, despite being now a fairly wealthy country, compared to some of the much poorer countries on this list, like the Democratic Republic of Congo, is still struggling with getting immunization coverage. Until recently, until maybe 3 or 4 years ago, most of the policy response to the problem of immunization has focused exclusively on supply, on making immunization services available. But the demand for immunization is likely also a key reason for low immunization rates in India, because now supply is actually quite good. Every village is within a short distance of an immunization camp. So this demand in terms kind of splits in two. One is core belief. In some places, people are deeply suspicious of immunization. There are very interesting papers on mistrust, which is something that we are going to have to reckon with, for example, when the COVID-19 vaccines comes in. So this is something that we will have to think about, and not just in India, but also in Europe and in the US. But it's only one part of the problem. There are also many people who say that they would love to get their kids immunized. They think immunization is a great thing, but they just haven't gotten around to do it. So, for example, in our setting in Haryana, in the north of India, in our surveys of parents, we find that upwards of 90% of parents, something like 95% of parents, would really like to get their kids immunized, but less than half have their kids fully immunized, of their kids having received 5 shots, according to their own report. So it seems that it's not just core belief, it's also getting it done. And for that, of course, nudges have been proposed coming out of behavioral economics. And there have been many experiments in the literature on various nudges. Small incentives, salience via SMS reminder, something that's already implemented in many countries and in particular in India on a very large scale. We've been proposing the use of immunization ambassador, find people who are influential in the social network and rely on them to spread the word, and caring as a lovely people on social rewards, that also lead to an increase in immunization in Sierra Leone. So many things have been proposed. And we got to a situation where the government of Haryana was willing to try out many of those, as many of those as we were willing to try, to identify one policy that they could scale on a limited budget. And so they really had two questions. Which of these, or which combination of these might work? Which variants? How high should the incentive be? Should it be increasing with each shot, or should it be flat? If we are going with immunization ambassadors, how to select them? Should they be selected in any particular way? We got the opportunity with their collaboration, full collaboration of the government, to try all of these things that are promising, to try them out on a fairly large scale, with the idea of picking what might work for scale up. So we had to work at scale because we wanted to make sure that we have all of the issues that may come up from scale up. And there was really two goals. One was to pick out of all of those possible experiments and possible interventions and their various variants, to pick the most effective and the most cost-effective combination. So the most effective is the one that increased immunization the most cost-effective is the one that increased the immunization the most per dollar spent. And ideally, we would find something that is actually cheaper, that reduces the cost per dollar spent compared to the status quo once you take into account all the fixed costs that there is in running an immunization camp. That was the first goal. That's not what I'm going to spend time on today, but we have a companion paper that focuses on that with Arun Chandrasekhar, Abhijit Banerjee, Matt Jackson, and others. And the second goal is to help find specific places where to run an effective but costly combination, which is what we are going to do in this paper. And in particular, see whether in those places, you can identify a set of places based on baseline characteristic exclusively, where it might actually be cost effective to do the most expensive thing, as opposed to stay with the status quo. So in this project, we had several treatments. We worked in 7 districts. We started by giving a tablet to the nurses and building a data collection infrastructure to help them enter all of the immunization they recorded, to record the data. So basically that system replaced the administrative data, and to test 3 domain interventions. What we tried is small incentive, mobile phone recharges that was also built on this platform, so very easy to implement, almost no administrative cost, just the cost of the incentive itself. We tried 4 variants of that, different levels, and was a flat payment for each shot versus increasing payment. The second type of intervention we tried is SMS reminders, either covering everyone, or either covering, 2/3 of the village, or covering 1/3 of the village. And then mobilizing the social network via immunization ambassadors. So people that are identified by their fellow villagers as influentials. And we then go to them and ask them if they are willing to become the ambassadors for the program. So every month, they receive a text message saying, hey, immunization is important. Continue to remind your colleagues that immunization is, your co-villagers that immunization is important. And there again, we have 4 ways of selecting the seeds. Either they are picked randomly, or they are picked to be information central, or what we have called gossips in previous work, or they are picked to be trusted, or they are picked to be both information central and trusted. So the incentive and reminder intervention covered 2,390 villages, but the social network intervention and the baselines, so what I'm going to talk about today, covered only 900 villages. So this is, and of course, when it covers a village, it covers the entire village, since everybody is eligible to the treatment in that place. This is a kind of a description, visual representation of the experimental design. Just a summary of what we did, just to tell you that there were many cells. We have incentives and then 4 types of incentives. Each of these is again cut between seed or no seed, and then different type of seeds, and then the SMS reminders. So this is how the server worked. So this was developed. We had to develop. Today, now the government has their own, which is probably better and richer than this one, but it didn't exist at the time. So we had to replace paper record by an electronic record, both to be able to run the intervention and also to be able to collect reliable data. So there was so the data was collected by the A&M at the same time, by the nurse at the same time as they run their camp. And then it went to the server, and then the server produced both reports for the nurses and for their supervisors, as well as the information that was necessary to give the mobile recharges and the SMS. The nice thing here is that the main source of data is administrative data from the servers on the number of children immunized, or in fact, by child. We have it as a child level. We have about 200,000 kids that entered the system. So that's a nice thing when you can use administrative data. We had to make sure this was valid. So we made a lot of effort of back checking to verify the quality of the data, and also to verify that kids who are not in our system are not immunized elsewhere. So just trust me that the data is actually reflects the actual immunization status in the village that we have. So all of this is back sort of backstory for what I'm going to show you now. But what is important is that the experiment was very complex. So many interaction, many variants. So in the companion paper, we developed a strategy to choose, again, based on machine learning, using the lasso, to choose the most effective and most cost-effective treatments. The most cost-effective program, that is the program that decreases the cost. In fact, it's the only program that decreases the cost per immunization globally relative to the status quo, is using this information hub, so people, the gossip, the village gossip, as ambassador for the program, plus SMS reminder. Both interventions are very, very cheap and increase immunization almost as much as anything else. So therefore, it's the most, at least anything else in isolation. So this we show is from that paper is the most cost-effective intervention. So that's nice. That is something that the government is actually ready to scale. And we are working with them to scale it up, at least in all of the districts with low immunization rates. Now, the most effective program, that is the program that increases immunization the most, is actually, maybe not surprisingly, but this is not something that came out of the data, a package treatment that combines everything. You need incentives. Fortunately, any level of incentives, as long as it's increasing with immunization, so you could take the low level of incentive, those immunization ambassadors and reminders. And that's actually, of course, the most expensive program, because with incentive, you end up giving a lot of money to many inframarginal people. And in fact, in this setting, globally, it's not cost effective. That is, it increases the cost per immunization compared to the status quo. You might still want to do it because it's a good thing to do, because you want immunization to go up, even if that's going to cost you a bit more. But beyond that, but then the government, basically the question of the government was, that's nice, but do we have a way to prioritize where we should do it? And in fact, once you're at it, maybe it would be cost effective in the kind of places where it is the most effective. So maybe, in fact, you would be in a position to say, look, don't do it everywhere, but do it in this set of villages. And then it will reduce your cost per shot, and it will also increase immunization a lot. So what we are doing in this paper is to look for heterogeneity in the package treatment effect on immunization, that big set of things. So now we are using we are aggregating the data a lot. We don't need the individual data per child for this at all. So our outcome variable becomes defined at the village level as the number of measles shots administered per month per village. We picked measles because it's the last immunization in the sequence, so it's a good marker for full immunization. D is the indicator B for this package treatment, and we compare the package treatment, which was administered in this very specific way in 25 villages, to 78 control villages. And these are these 38 baseline village level characteristics. So you see that even though we start from a lot of data, once we look at the village level variable in these restricted packages, it's suitably aggregated. It's really only 25 villages in the treatment, 78 in the control. So that's smaller than the number of, it's the same order of magnitude as Z, and certainly smaller once you start interacting everything with everything. So it is a setting where you do need to use the machine learning algorithms. Some descriptive statistics. The one in bold at the beginning is the outcome. So it tells you that immunization increased in the treatment group compared to the control group by about a little less than 3, 2.5. The rest are baseline variable, and you don't need to look at all of them. They are similar in treatment and control group. What's maybe the most relevant is that if we look at the older brothers and sisters of kids who would be in our sample, among them, less than half have received 5 or more vaccines according to the report of the parents, which is almost surely a big overestimate, because in previous work I have shown that parents just over-report immunization compared to what they have actually received. So that's at most half of the kids were fully immunized, and the number is probably much lower than that. So we have our average treatment effect of about 2.5. Now we're going into the implementation of the heterogeneity analysis. So there are 4 ML methods we tried. This is some details on how we run them. We try to use two-way interaction between the variables there in the elastic nets. We have a cross-validation. We include district time fixed effect, village level, and weight all village by village population. For our confidence interval, we have 250 random splits by half. And what I'm going to report is alpha of 0.05, which means actually a 10% significant level. So something which I skipped is that you can use some characteristic to pick the method that works the best. In this case, it's elastic net and neural network. So that's what I'm going to continue looking forward for these two methods. So first thing is what's the best linear predictor of the cat of the package treatment? And you find for elastic net average treatment effect of 3, and heterogeneity loading coefficient of 1. Which basically we can't reject that our proxy predictor predict almost perfectly the heterogeneity in the data. So it's very, very significant. So in this setting, it does look like we have a strong heterogeneity in the treatment effect that is nicely picked up by our ML proxies predictors and by some combination of these. So that's encouraging. This is what we get from the grouped average treatment effect. So the places where the treatment is most effective actually have an increase in immunization per month of about 10. The places where it's least effective have an effect of -8. So actually a quite significant negative impact in the least affected places. So they are affected, they are just affected the wrong way. This is something that we are finding the same thing of large positive effect for the most affected group in the elastic net and large negative effect for the elastic net specification as well. So just to put them, just comparing this most affected and least affected group, you can see that the average treatment effect for the most affected group is 11 immunization. The baseline, using the first methods, the baseline immunization rate in that group for the villages in that group is estimated to be about 3.8. So this is a big increase. It's about a 300% increase in immunization. So you might wonder whether that's even plausible. Meanwhile, in the least affected group, we estimate a larger control mean of 12 immunization per month and a decline, which is significant, of -7. So let me discuss a little bit these two numbers. So first of all, for the most affected group, is it plausible to have an increase of 300% in immunization? So in our previous work on incentives, which was done in Rajasthan, we found that compared to a setting where there is absolutely perfect immunization services, incentive increased complete immunization from 16% to 38%. So the order of magnitude is very much the same. It's like a multiplying factor. And this was a region with very low immunization rate as well, even lower, since even after the incentive, we only reached 38%, whereas here we started at a mean of maybe around 40%. So this is very much the same order of magnitude. If you remember, if we look at this group of villages, parents in this group, I'll show that to you in the C-line in a minute, report that an immunization rate of 38%. So they report that 38% of the kids have gotten 5 shots or more among the older children. The quadrupling would imply a number above 1, but remember that the 38% is almost surely a very large overestimate. So again, it's actually not crazy to think that it's possible, that you can have very large effect from incentives. And certainly the order of magnitude doesn't seem unreasonable to me at all. The level are so low to start with that it's not very hard to multiply them as opposed to increase by 5% or something like that. Now, for the least affected group, what we find is a decrease in immunization. So is that plausible? Again, this is something that certainly I did not expect, and I'm not, happy about. But there is a literature that would certainly suggest that it is possible. So the incentives are very, very small. There is work from Gnisi and others showing that small incentives can decrease intrinsic motivation. And in particular, in this setting, trust in immunization is delicate. So perhaps people are starting to wonder why the government needs to pay them to do this if they were doing it already. Regardless, that's actually a very important result that needs to be probed, both sort of conceptually and for policy purpose. It highlights the importance of looking for heterogeneity when conducting experiments that are meant to guide policies, particularly for looking for heterogeneity around things that that the policymaker can target. Because now what the policymaker can do is certainly avoid the type of villages where the effects are negative, which we wouldn't have known otherwise. And this is where the C-line can be useful. And what comes out of the C-line, really what jumps out of it very strongly without having the need to look at many things, is that by all the previous indicators of past immunization, the villages where the effects are positive and large are the effect where immunization rates were lower to start with. And the villages where the effects are negative are the effect where the villages where immunization was low to start with. I want to emphasize there is nothing mechanical in these results because it's not that the villages that are higher immunization have such high immunization that they were top coded and there was nowhere to go. The immunization rate, full immunization rate was 49.9% in the in the least affected group at baseline. So they had, they had plenty of chances to increase their immunization. In fact, I went back to looking at our pre-analysis plan where we wrote something, this was before this paper was developed that we wrote the pre-analysis plan. We wrote something vague to the effect that we were going to look at heterogeneity by some baseline variable. And we did not indicate baseline immunization rate as one core variable we would look at. That's surely an oversight, but that's, at least to us, who were completely immersed in this is not something that jumped at us. This is not something that jumped at the government, who was much more interested in religious variable or quality of implementation or things like that. So it might seem completely obvious once it's done, but it wasn't obvious ex ante, at least to us, and it's also not mechanical. So the policy recommendation, of course, is to prioritize these villages under budget constraint. And if you do that, what is nice is that your previous, previously we had calculated when we looked at the cost per, the number of immunization you're getting per dollars, including all of the cost of running a camp and the cost of the vaccine themselves and paying nurses, etc., for which we have collected very, very detailed data. This package is expensive enough that the cost per immunization on average increases when you implement it, mainly because you end up giving incentives to a lot of people who would have getting immunized anyways. So if you count the incentive as transfers, of course you would be fine, but I have not managed to persuade the government that this is how they should think about it. So for them, the incentive is the cost. So what is interesting is that if you look at the two most affected groups, the number of immunization you're getting per dollars in the treatment and in the control group is actually almost identical. So the policy is just as cost effective as the status quo for the most affected group, the demographic which has the largest impact. So you have this group of villages which we can pinpoint, we can tell who they are, the type of villages they are based on their baseline characteristics. They are the most disadvantaged village to start with. I haven't shown you, but in addition from having low immunization, they're also poorer. They have low immunization to start with. And there you have not only largest effect, but you have a program that breaks even from the point of view of cost per immunization. So this is something that we would not have known if we had not run this analysis. And that completely, that is a very important message to convey to our partner, because it does change the outlook that they have on this particular package intervention, which otherwise they would have dismissed, saying, well, we're not going to do that. We are just going to do the things that cost effective globally. So in conclusion, what we are doing in this paper is to provide a method to discover heterogeneity in a disciplined way. Of course, this doesn't come for free. A concern in application is power loss due to data splitting. And if you're applying this method to data that you've collected before without thinking of powering the study for the discovery of heterogeneity, you might be disappointed. You might have a lot more noise than you would wish to have. We do see this loss as the price you have to pay when you're not certain or not willing to specify ex ante the form of the heterogeneity. And it's often the case because, economic theory doesn't always give us a guide about where to look for heterogeneity. Sometimes at early stages, you cannot take a stand. So if you can know in advance where the heterogeneity is likely to be and likely to be interested, then by all means specify it in your analysis plan. But if it's not, then this will, if you want to look for it ex post, looking this type of methods, then you have to roughly budget a sample size that is about double the size that you would normally have. We showed that this method has interesting and important results in one application on the demand for immunization in India, where the discovery of heterogeneity leads us to actionable policy recommendations. Thank you very much for your attention, and I wish you a wonderful conference.